Merhaba arkadaşlar. Günaydın. Umarım hepiniz iyisinizdir. Geçtiğimiz hafta işletim sistemi konseptleri hakkında konuşmuştuk ve bir giriş yapmıştık. Prosesler hakkında konuşmaya başlamadan önce aslında e, bir giriş bölümü olarak görebileceğimiz bir bölümümüz daha var. Bu hafta işletim sistemi yapılarından ve işletim sistemi servislerinden bahsedeceğiz. Eğer başlamadan önce bir sorunuz yoksa doğrudan giriyorum. Var mı sorusu olan? Okay then. This week we will cover operating system structures. We can view an operating system from several different points. One view focus on the services that the system provides, and another on the interface that it makes available to users and programmers. And the third on its components and their interconnections. So basically, we can categorize these views on three different sections. The first one is system, the second one is the interface, and the third one is the interconnections and components. In this chapter, we are going to explore all these aspects of operating systems, showing the viewpoints of users, programmers, and operating system designers. So let's start with operating system services. An operating system provides an environment for the execution of programs. It makes certain services available to programs and to the users of those programs. The specific services provided, of course, differ from one operating system to another, but we can identify common classes. One set of operating system services provides functions that are helpful to the users. Almost all operating systems have a user interface. This interface can take several different forms. Most commonly, a graphical user interface is used. As you know, in graphical user interface, the interface is a window system with a mouse that serves as a pointing device to direct input-output operation, choose from menus and make selections, and a keyboard to enter the text. Mobile systems, such as phones and tablets, provide a touchscreen interface, which enable users to slide their fingers across the screen or press buttons on the screen to select choices. Another option is a command line interface, which uses text comments and a method for entering that comments. Also, some systems provide two or all three of these versions. The next service is program execution. The system must be able to load a program into memory and to run that program. The program must be able to end its execution either normally or abnormally. Also, we need I/O operations. A running program may require input-output, which may involve a file or an I/O device. So this part is important. While we are discussing the input-output operations, please do not forget that file operations are also part of input-output operations, not just entering the text or showing messages to the screen. Also, file operations are part of input-output system. For specific devices, special functions may be desired. For efficiency and protection, users usually cannot control input-output devices directly. Therefore, the operating system must provide a medium to do input-output. With the input-output services, an operating system has to provide some services for file system manipulation too. Obviously, programs need to read and write files and directories, and they also need to create and delete them by name search for a given file and list file operations, list file information. So to create these services, operating system has to provide a medium to users. The next service can be considered as communication. There are many circumstances in which one process needs exchange information with another process. Such communication may occur between processes that are executing on the same computer or between processes that are executing on different computer systems which tied together by a network. We have two main methods for that. Communications may be implemented via shared memory, which two or more processes read and write to a shared section of memory, or message passing, in which packets of information in predefined formats are moved between processes by the operating system. And the last service in this set is error detection. The operating system needs to be detecting and correcting errors constantly, because errors may occur in the central processing unit and memory hardware in input-output devices and in the user programs. For each type of error, the operating system should take the proper action to ensure correct and consistent computing. Okay, this was the first set. In the first set, we have user interface, program execution, I/O operations, file system manipulation, communications, and error detection. Another set of operating system functions exist for not for helping the user, but rather for ensuring the efficient operation of the system itself. So these are not for the direct use of users, but we can categorize these services to ensure the efficient operation of the system itself, which are resource allocation, logging, protection, and security. When there are multiple processes running at the same time, resources must be allocated to each of them. The operating system manages many different types of resources. Some, such as central processing cycles, main memory, and file storage, may have spatial allocation code, whereas others, such as input-output devices, may have a much more general request and release codes. We want to keep track of which programs use how much and what kinds of computer resources for this resource allocation. So we need a logging mechanism. We need to log the resources, which devices or which let's say CPUs, main memory, and file storage or I/O devices, which of them are allocated for which process. So for that reason, we need a logging mechanism. Also, last week we have discussed what are the meanings of protection and security terms. So an operating system provides a healthy protection and security services to its users. So this is the second set of system services. Here you can see a view of the various operating system services and how they interrelate. So note that these services also make the programming task easier for the programmer, because we have hardware at the base level. We have an operating system between the hardware and user and other operating systems, other system programs. And this operating system has some functions such as program execution, I/O operations, file system, communication, resource allocation, accounting, error detection, protection and security, etc. So these are the services provided by operating system. So using system calls and user interfaces, user and other system programs can use that hardware resources through operating system. or through operating system services. So this is Avivo operating system services. We already mentioned that there are several ways for users to interface with the operating system. Here, we are going to discuss three fundamental approaches. One provides a command line interface or command interpreter that allows users to directly enter commands to be performed by the operating system. The other two allow users to interface with the operating system using a graphical user interface. We'll start with command line interpreter. Most operating systems, including Linux, Unix, and Windows, treat the command interpreter as a special program that is running when a process is initiated or when a user first logs on. On systems with multiple command interpreters to choose from, the interpreters are known as shells. Most shells provide similar functionality, but you can choose one of them on your operating system. The main function of the command interpreter is to get and execute the next user-specified command. Many of the commands given at this level are manipulates files. Basically, you can create, delete, list, print, copy, execute using that files using command line interpreter. A second strategy for interfacing with the operating system is through a user-friendly graphical user interface. Here, rather than entering commands directly using a command line interface or a console or a prompter, users employ a mouse-based window and menu system characterized as a desktop metaphor. The user moves the mouse position, its pointer on images, icons, or direct to the screen. And in this case, we can call that screen as a desktop. That represents programs, files, directories, and system functions. Depending on the mouse pointer's position or location, clicking a button on the mouse can invoke a program, select a file or directory, known as a folder in this case, or pull down a menu that contains commands, and you can click another command using that menu. So it's generally described as desktop metaphor, but in general, we can call it as a graphical user interface. In these days, we have to handle another interface because command line interface or a mouse and keyboard system is impractical for most mobile devices. Typically, they use just touchscreen interface. Here, users interact by making gestures on the touchscreen. For example, pressing and swiping fingers across the screen. Although earlier smartphones, some of you may remember that, the earlier smartphones include a physical keyboard, but most smartphones and tablets now simulate a keyboard on the touchscreen. We don't have a physical keyboard, just using a simulation on the touchscreen. So still, this is a graphical user interface, but we don't have a direct desktop metaphor here. So it's a bit different from our desktops, our classical graphical user interfaces. Okay, now we know system services and we know the user interfaces. So between the system functions and user interfaces, we have system calls. You can remember, you can call that, let's say, figure here. We have an operating system. In the operating system, we have operating system services, and we have user interfaces. And between user interfaces and operating system services, we have system calls. Now we are going to dive on system calls. System calls provide an interface to the services made available by an operating system. These calls are generally available as functions written in C and C++, but some certain low-level tasks may have to be written using assembly language instructions, but generally they are written in C or C++. Most system calls accessed by programs using a high-level application programming interface, so you don't need to directly know all codes written in C or assembly, because the operating system provides you an application programming interface, and using that application programming interface, you can use system calls. We have three most common APIs, which are Win32 API for Windows, POSIX API for POSIX-based systems, including all versions of Unix, Linux, and Mac OS, and we have Java API for the Java virtual machines. So we have three most common APIs we can discuss. But we are going to focus on mainly Win32 and POSIX. Before we discuss how an operating system makes system calls available, let's first use an example to illustrate how system calls are used. So here we are going to write a simple program to read data from one file and copy them to another file. So let's assume that you have a simple C program. On that program, you are going to read some data from a file, and you are going to write the same data to another file. So this is our scenario. So the first input that the program will need is the names of the two files, the input file and the output file, based on our example scenario. These names can be specified in many ways, depending on the operating system design. For example, one approach is for the program to ask the user for the names. In an interactive system, this approach will require a sequence of system calls. First, to write a prompting message on the screen, and then you have to read from keyboard the characters that define the two file names. This sequence requires many input-output system calls. Okay, you are just print a simple sentence to screen, and based on that message, you are going to read some data from keyboard. As an application program developer, it's an easy task, but in the backline of that call, that simple sequence, we have lots of different input-output system calls. Once the two file names have been obtained, the program must open the input file and create and open the output file. Each of these operations requires another system call. When both files are set up, we enter a loop that reads from the input file, which is a system call, and writes to the output file, which is another system call. Finally, after the entire file is copied, the program may close both files, which are two system calls too. Write a message to the console or window, which are more system calls, and finally terminate normally, the final system call. So this system call sequence, as shown in this figure, as you can see, we have lots of system calls. So as you can see, even a simple program like that may make heavy use of operating systems. So generally, systems execute thousands of system calls per second, because as you can see, such a simple program needs lots of operating system intervention. Operating system has to provide that interfaces for that application program. For that reason, generally, operating system execute thousands of system calls per second for different services, for different applications, or for different users. So this is the example how system calls work and how system calls used on application programs. But as you can guess, most of the programmers never see this level of detail. Generally, application developers design programs according to an application programming interface, or we can call it as API. Another important factor in handling system calls is the runtime environment. The full suite of software needed to execute applications written in a given programming language, including its compilers or interpreters, as well as other software, such as libraries and loaders. We can call that environment as runtime environment. The runtime environment provides a system call interface that serves as the link to the system calls made available by operating system. The system call interface intercepts function calls in the API and invokes the necessary system calls within the operating system. The system call interface, we already mentioned that. Typically, a number is associated with each system call, and the system call interface maintains a table indexed according to these numbers. The system call interface then invokes the intended system call in the operating system kernel and returns the status of the system call. So the caller need know nothing about how the system call is implemented or what it does during execution. The caller need only obey the API and understand what the operating system will do as a result of execution of that system call. Thus, most of the details of the operating system interface are hidden from the programmer by the API and managed by the runtime environment. Okay, we already know that lots of details are hidden from the end users, but also that functionalities, that details are hidden from the programmer too. Most of the details of the operating system interface or system calls or functions are hidden from programmer. We can use that functionalities just using the API or runtime environment. But still, it's good to know how they work. Here you can see the relationship between an API and the user application, or the system call interface and the operating system can be seen in this figure, which illustrates how the operating system handles user application invoking the open system call. So let's assume that we have an user application. That application wants to open a file. So it's going to call a system call, let's say open in this case, using system call interface. We have an API, and that API declares that you can use open function or open call to open a file. And based on that, I'm going to open that file and I'm going to return you to information. So using system call interface on the user mode, we can call open system call. When the operating system gets a system call, it has to switch the mode to kernel mode. On the kernel mode, every system call has a number, let's say an index, and based on index we can find the related functionality or related procedure, related code for that system call. So based on the open call on the kernel mode, the operating system is going to find the correct location, and at that location we have a function, we have a procedure to open a file. So it's going to open the file and return the information to the user application, which switch the user mode again. So as you can see, user application does not need to, or user application developer does not need to know the details on the kernel mode. We can just use the system call to get the information from an open file. So this is how the API, system call, and operating system relationship works using runtime environment. Okay, now we know what the system call is, but in most cases, we have to pass parameters with system calls too. Let's remember the previous example. On the previous example, we assume that we are going to open a file. So, okay, the function is open, but we have to pass a parameter, which is obviously will be the location of the file we want to open. So we can say that system calls occur in different ways, depending on the computer in use. Often, more information is required than simply identity of desired system call. The exact type and amount of information may be differ according to the particular operating system and the used call. But we have three general methods to pass parameters to the operating system. Okay, so we are on the user mode. We want to call a system function, so we want to use a system call. And to make that operation, we have to pass some information to operating system because it's going to switch the mode to kernel mode. So we have to provide some details. We have to provide some informations with the system call to operating system. So we have three main methods for that. The simplest approach is to pass the parameters in registers. However, in some cases, there may be more parameters than registers. So this is the simplest way. Okay, I'm going to pass the parameters to operating system. So on the user mode, I can write that information to registers. So on the kernel mode, operating system directly access the registers and use that information. This is the simplest way, but in most cases, the information we want to pass is has a greater size than the registers. So in these cases, the parameters are generally stored in a block or a table in memory. So instead of just writing registers, we can write the information on memory, and we can pass the address of that memory location using registers again. So instead of writing the parameters directly to registers, I'm going to write the parameters or information to the memory, and I'm going to write the address of that memory space to registers. So I can pass that information using that. Parameters also can be placed or pushed into a stack by the program and popped off the stack by the operating system. So instead of using an undefined space and passing the address of it, we can directly use a predefined stack. So user application push the information to that stack and operating system pop that information from the stack. So we can use that method too. Some operating systems prefer the block or stack method because those approaches do not limit the number of length of the parameters being passed. If you want to use the simplest method, if you want to use just the registers, you have a limitation based on the size of your registers. But if you use the memory block or if you use the stack, basically the limit of that information will be the same as the limit of your memory. So you can pass more parameters, more number or more length of parameters being passed. You can use them as being passed. Here you can see an example of passing parameters as a table. At left, we have a user program. User program wants to call a system call. Let's say we are going to call the system call 13 here, but also we want to pass some parameters too. So in this case, this is the second way, the block way we discussed. We can write the information, the needed information or the parameters to memory on our user program, and we can get the address of that block, and we can write that address to the register and make the system call. System call, let's say 13. 13 is the index, and based on 13, we are going, actually, operating system is going to execute a predefined procedure. And on that procedure, operating system can access the register and get the address of parameters for call, and using that address can get the parameters from memory and use that parameters in its, let's say, system call procedure. And that's how parameters can be passed by operating system using a table or a memory block. Any question?
Hocam burayı tekrar anlatabilir misiniz?
Okay. We know that we can use system calls to access the system, operating system functionalities. Let's assume that our user program wants to open a file. Okay, so we cannot directly access the input-output devices because they work on kernel mode. Our user applications works on user mode. So when we want to open a file, we have to use the API provided by the operating system. So that API provides us some system calls to access the operating system functionalities. If we want to open a file, we can use open system call. So in most cases, that system call needs some parameters too. So if assume that you want to open a file, okay, open is the system call, but also you have to provide the, let's say, location of the file, the file open mode, etc. You have to pass some parameters. So we have three main ways to pass parameters to operating system because our application program and the operating system works on different modes. So this is actually the way how you can pass parameters from user mode to kernel mode. The simplest way is writing to registers because both the application programs and the operating systems can reach the registers of your system, of your computer system. So the basic way is to write the parameter to register on the user program so operating system can access that data, that parameter, directly using registers. But in most cases, we have to pass more parameters which fits or suits to registers. Registers has a limited size. So if we want to pass more parameters as number or length, we have to use another method. We have two different methods for that too. First is the passing via table, which is illustrated in this figure. Instead of writing the parameters directly to the register, we can write our parameters to a block on the memory or in a table on the memory, and we can write the address of that memory space to register. So operating system can read the address of the register, address of the table from register, and directly access that parameters. The third way is we know that operating system and user program use the shared memory. We can define a data structure on that shared memory as a stack. So the user programs and operating system use the same stack. User program pop the parameters to a stack and operating system push that parameters, pop that parameters from the stack. So basically, these are to creating creating a communication mechanism between user programs and operating systems. Okay?
Teşekkür ederim.
So we're continuing with the types of system calls. System calls can be grouped into 6 major categories, which are process control, file management, device management, information maintenance, communications, and protection. Now we are going to briefly cover the types of system calls that may be provided by an operating system. The first one is, as I said, process control. On the process control, we can create processes, terminate processes, and or abort processes. Also, we have to load or execute processes too. And in some cases, we need to get or set some information. So get process attributes and set process attributes also part of process control. In some cases, we need to wait for time, wait for an event or a signal. Also, we need to allocate the the memory, or we need to free the memory after execution. We need to dump memory if we had an error. We need debugger for determining bugs, single-step execution, and we need some logs mechanism for managing access to shared data between processes. So these system calls for these mechanisms can be categorized as the first type of system calls, which is called as process control. If you want to control the processes, actually, if your operating system wants to provide a mechanism to you to use process control, it has to provide these mechanisms. It has to provide some system calls for these mechanisms to you or to programmer. The second one is file management. On the file management, we need some mechanisms we need some system calls for creating a file, deleting a file, open or close a file, read, write, or reposition on a file, get and set file attributes. So the operating system, actually the API, has to provide some system calls to application developers for file management. Also, it has to create some mechanisms. It has to provide some system calls to device management too. On device management, we need request a device, release a device, read, write, or reposition on device, similar to file management, get device attributes or set device attributes. Also, logically, we can attach or deattach that device to the system. So these are the system calls which has to be provided by operating systems to application developers. The fourth one is information maintenance. On the information maintenance, we need some system calls to get or set time, get system data or set system data, get and set processes, files, or device attributes. So these getting or setting attributes are also part of the information management. Also, we need some system calls for communication. On that case, we need to create or delete communication connections, send and receive messages, transfer status information, and again, we need some mechanism to attach and deattach remote devices, because remote devices means we created a network, so it's a part of communication too. And the last one is protection. On the protection type of system calls, we need control access to resources, get and set permissions, and allow and deny user accesses. So these are the types of system calls. Actually, we have loads of system calls on different APIs on different operating systems, but basically we can categorize them as these 6 types. On here we have process control, file management, device management, information maintenance, communication, and protection. Here, this figure summarizes the types of system calls provided by an operating system. So we are focusing on Win32 on Windows side and POSIX on the Unix and Linux side. And we have some examples. So on process control, if you want to create a new process on Windows, you can use create process system call. If you are on Unix, Linux, or Mac OS, you can use fork to create a process. So let's assume that you want to create a communication line, you want to create a pipe. On Win32 side, on Windows side, you can directly use create pipe system call, or on the Unix side, on the POSIX side, actually, you can directly use pipe system call to create a pipe. So these are the examples of Windows and Unix system calls you can use directly on your operating systems. Any question? Okay, then let's take a break. I'll be here in 10 minutes. See you.